Welcome. You've arrived at this quiet hour and we're glad you're here. Tonight we're going to explore something that doesn't often appear in history books. Not the battles themselves, but the hours between them. The moments when soldiers tried to rest in conditions that seemed designed to prevent it entirely. This is the story of winter nights during World War II, specifically the winters of 1944 and 1945. In the forests of the Ardennes and across the frozen landscapes of the Eastern Front, men dug holes in frozen ground and tried to sleep while temperatures dropped to 10 degrees Fahrenheit, sometimes far lower. They were cold, they were wet, and they were expected to remain alert through the darkness. How did they manage it? How did they find warmth when a visible flame could mean death? How did they rest when rest seemed impossible? There were no miracles here, no single solution. What emerged was a collection of small techniques, improvised methods, and partnerships between soldiers who learned to keep each other alive through the long hours of winter darkness. So settle in, let the day fade. We're going to move slowly through one night in a foxhole, from the moment the light begins to fail until dawn arrives again. The winter of 1944 arrived with a particular intensity. Soldiers described it as if Old Man Winter were making up for milder seasons, arriving with snowstorms so heavy they seemed to bury any promise of spring beneath white drifts that accumulated day after day. In the Ardennes forest, temperatures fell to 10 degrees Fahrenheit. That alone would have been manageable under different circumstances. In a home, with walls and a stove, with dry clothing and warm food. But these were not different circumstances. These were the front lines, where men lived in holes dug into the earth, where everything was damp, where the wind moved freely through the trees and across open ground. Further east on the Soviet front, the cold was even more severe. Temperatures dropped to 60 degrees below 0 Fahrenheit. At that temperature, the air itself changes. It becomes so clear and still that sound carries in strange ways. A man chopping wood could be heard 10 miles away. This meant that even the smallest noise, a cough, the scrape of a shovel, the click of a rifle bolt, had to be managed carefully. The silence was not peaceful. It was mandatory. The landscape transformed under this cold. Snow accumulated in drifts that reshaped the contours of the land. Trees stood bare and dark against white ground. Visibility often collapsed to just a few yards as ground fog rolled in, thick and grey, turning the world into a small circle of awareness. Beyond that circle, there was only whiteness and the sound of wind moving through branches. For the soldiers stationed in these conditions, the cold was not an inconvenience. It was a primary threat, as dangerous as enemy fire in its own way. Hypothermia could kill just as efficiently as a bullet, and it worked slowly, stealing warmth degree by degree until a man simply stopped functioning. The human body maintains a core temperature of approximately 98.6 degrees Fahrenheit. When that temperature begins to drop, the body responds with shivering, an attempt to generate heat through muscle movement. But shivering requires energy, and energy requires food, and food was not always abundant on the front lines. A soldier who was cold, wet, and hungry was fighting a losing battle against thermodynamics. The environment dictated everything. When night fell, the temperature dropped further. The hours of darkness were the coldest, and they were also the hours when soldiers were most vulnerable. Exhausted from a day of combat or labour, they needed rest. But rest meant stillness, and stillness meant the body stopped generating heat through movement. This was the fundamental problem. How to sleep when sleeping meant becoming cold, and becoming cold meant risking death. The winter also brought moisture. Snow melted during the day when temperatures rose slightly, then froze again at night. Rain fell and mixed with snow, creating a cold slush that soaked through clothing and equipment. Soldiers described feeling as though they were being sprayed with water for 10 hours at a time. Everything was damp. Uniforms, blankets, boots, all of it absorbed moisture from the air and the ground, and damp fabric loses its ability to insulate. Add to this the fog. It rolled in thick and low, reducing visibility to 6 feet or less. A soldier could not see beyond the immediate space around his foxhole. The world contracted to a small bubble of grey air and frozen ground. In this fog, the front line became a series of isolated positions, each man or pair of men alone in their hole, unable to see their comrades, unable to see the enemy. The fog carried sound strangely. Sometimes it muffled everything, creating an eerie silence. Other times it seemed to amplify distant noises, the rumble of artillery, the crack of a rifle, voices calling in languages the soldiers could not understand. The psychological effect of this isolation was significant. Each foxhole became its own small world, cut off from the larger war, focused entirely on the immediate problems of warmth and survival. The cold affected more than just the men. Equipment failed. Lubricants in rifles and machine guns thickened or froze entirely, causing weapons to jam. Vehicle radiators cracked as coolant froze and expanded. Fuel lines clogged with waxed diesel. Artillery recoil systems became sluggish as hydraulic fluids turned viscous. Even simple tools became difficult to use. Metal handles burned exposed skin with cold, and fingers grew numb and clumsy inside gloves. So the soldiers adapted. They learned to strip weapons and relubricate them with lighter oils that would not freeze. They learned to keep vehicle engines idling through the night to prevent them from seizing. They learned to warm ammunition before loading it, because cold ammunition sometimes failed to fire reliably. But these were mechanical problems with mechanical solutions. The problem of sleeping, of keeping a human body warm and functional through the hours of winter darkness, required different thinking entirely. The night began with sunset, which came early in December. By 4 in the afternoon, the light was already fading. By 5, it was full dark. That meant 15 hours of darkness, 15 hours when the temperature would continue to drop, 15 hours when a soldier might be called upon to fight or to simply stay alive in his hole. 15 hours is a long time to be cold. Before a soldier could think about sleeping, he had to create a place to sleep. In theory, this was straightforward. Dig a hole, get below ground level, use the earth itself as shelter. In practice, the frozen ground made this one of the most physically demanding tasks of winter warfare. The standard entrenching tool issued to infantry was a small folding shovel with a blade approximately 6 inches wide. In normal soil, a soldier could dig a fighting position in perhaps 30 to 45 minutes of hard work. In frozen ground, that same hole might take 3 or 4 hours. The earth was not simply cold, it was frozen solid to a depth of several inches, sometimes more than a foot. The surface layer had transformed into something closer to rock than soil. A shovel blade would strike the ground and bounce back, barely leaving a mark. The soldier would have to swing the tool like a pick, using the corner of the blade to chip away at the frozen crust, breaking it into chunks that could then be pried loose and removed. This was exhausting work. It generated heat through exertion, which was welcome at first, but it also caused sweating. Sweat-dampened clothing would then chill rapidly when the soldier stopped to rest, creating a cycle of overheating and dangerous cooling. Soldiers learned to pace themselves, to work steadily without pushing to the point of heavy perspiration. The noise was another concern. Metal striking frozen earth makes a distinctive sound, a hard, ringing impact that carries across open ground. In areas close to enemy positions, soldiers had to dig as quietly as possible, sometimes using only their hands or improvised wooden tools to avoid drawing fire. This made the work even slower. The goal was to create a hole roughly 8 feet long, 4 feet wide, and 4 feet deep. These dimensions were not arbitrary. 8 feet allowed 2 men to lie down end to end or side by side with some room to move. 4 feet of width provided enough space to sit, turn, and access equipment. 4 feet of depth put the soldiers below ground level, providing protection from small arms fire and shell fragments, while still allowing them to fire their weapons over the edge. But reaching that depth through frozen soil was a victory in itself. Some soldiers never managed to complete a full foxhole before darkness fell, or before they were called to move to a different position. They would dig as deep as they could, 2 feet, 3 feet, and accept that partial shelter was better than none. The removed earth presented its own problem. In normal conditions, the excavated soil would be piled around the edges of the hole, creating a low berm that provided additional protection. But frozen chunks of earth did not pile neatly. They were irregular, difficult to stack, and they did not compact into a solid barrier. Soldiers learned to use the chunks strategically, placing larger pieces where they would provide the most cover and filling gaps with smaller fragments. As the hole deepened, the work became more difficult. The soldier was now standing in a pit, swinging a short-handled tool in a confined space, trying to break frozen earth while bent at an awkward angle. The muscles of the back and shoulders took the brunt of this labour. Men would trade off, one, digging while the other rested or stood watch, then switching when the first became too exhausted to continue effectively. Sometimes the ground would reveal obstacles. Rocks embedded in the soil had to be pried loose or dug around. Tree roots, though less common in winter when growth had stopped, still presented barriers that required cutting with a hand axe, or simply accepting as part of the whole structure. In some cases, soldiers would intentionally dig near trees, using the root system to reinforce the walls of their foxhole. The frozen ground did have one advantage. It held its shape well. A hole dug in frozen earth was less likely to collapse than one dug in softer soil. The walls stood firm without needing constant maintenance or reinforcement. This stability was important because the soldier would be living in this hole for an indefinite period. Days, sometimes weeks, and a collapse could mean being buried or at least losing the protection the hole provided. Once the basic excavation was complete, the soldier would begin to refine the space. The floor of the hole rarely ended up level. The process of chipping away frozen earth created an uneven surface with ridges and depressions. Using the shovel blade, the soldier would try to flatten the floor as much as possible, creating a more comfortable base for sleeping. But even a flat floor was still frozen earth, and frozen earth conducts heat away from the body with brutal efficiency. Lying directly on that surface would chill a soldier to the point of hypothermia within a few hours. This meant that the floor needed treatment, needed some kind of insulation layer that would break the thermal connection between body and ground. The walls too required attention. The rough surface left by the digging process would shed dirt and ice crystals whenever the soldier moved or bumped against them. Over time, this debris would accumulate on the floor, mixing with any water that seeped in to create cold mud. Soldiers would sometimes try to smooth the walls, scraping them with the shovel blade to create a more finished surface, though this was rarely a priority compared to other survival tasks. The effort required to create this space cannot be overstated. After hours of digging in freezing temperatures, after breaking through frozen earth one chip at a time, the soldier was already exhausted before the night even began. His hands would be blistered despite gloves. His shoulders would ache. His back would be stiff from the repetitive motion of swinging the shovel, and this was just the beginning. The hole was dug, the space was created, but it was still just a hole in frozen ground. It was not yet a place where a person could survive the night. That transformation, from excavation to shelter, required additional steps, additional modifications that would determine whether the soldier would wake up in the morning or slowly lose consciousness to the cold during the dark hours. The ground had resisted, but the soldiers had persisted. Now they had a space below ground level, a small volume of earth that belonged to them. What they did with that space in the hours ahead would make all the difference. 8 feet by 4 feet by 4 feet. These were the dimensions of survival. This was the space in which a soldier would spend not just one night, but many nights. It would become more familiar to him than any bedroom he had ever known, because his life depended on understanding every inch of it. The shape was essentially rectangular, though rarely perfect. The process of digging through frozen earth did not allow for precision. Corners might be rounded, walls might lean slightly inward or outward, the floor might slope toward one end. But the approximate dimensions remained consistent across different units and different armies. This was not coincidence. These proportions had been established through hard experience as the minimum space required for 2 men to function as a fighting unit while also having room to rest. 2 men because that was the basic tactical element of infantry warfare. The buddy system was not just about companionship or morale, it was about survival and effectiveness. 1 man alone in a foxhole faced impossible demands. He could not maintain watch continuously. He could not stay alert through an entire night without sleep. He could not treat his own injuries or check his own extremities for frostbite. 2 men solved these problems. They could alternate watches, share body heat, and care for each other when care was needed. The 8-foot length allowed for multiple configurations. The 2 men could lie head to toe, giving each person approximately 4 feet of length to curl up in. Or they could lie side by side, which was more efficient for sharing warmth, but required them to coordinate any movement. During watches, one man might sit at one end with his weapon ready, while the other slept at the opposite end, creating as much separation as the space allowed. The 4-foot width was narrow by any civilian standard, but it served its purpose. It was wide enough for a soldier to turn over without climbing out of the hole. It allowed room for essential equipment, a rifle, ammunition, rations, water, to be stored within arm's reach. But it was not so wide that it required excessive digging through frozen earth, and it was not so wide that a single soldier could not reach across it to access something on the far side. The 4-foot depth was perhaps the most critical dimension. It had to be deep enough to provide protection. A soldier standing in a 4-foot hole could crouch down and have his head below ground level, safe from rifle fire passing overhead. But the hole also could not be too deep. A deeper hole would be harder to exit quickly if the soldier needed to move. It would also be colder, as cold air sinks and deeper depressions trap it more effectively. This space was not just a military position. It became a home in the most literal sense, the place where a person ate, slept, and lived. Soldiers would begin to organise the space with an instinct that matched any domestic arrangement. One corner might become the designated spot for rations, another corner for ammunition, personal items, letters from home, photographs, a spare pair of socks would be kept in the driest area, often wrapped in whatever waterproof material was available. The psychology of living in this space was complex. On one hand, it provided a sense of shelter, a feeling of being contained and protected. The earth walls created a boundary between the soldier and the hostile world beyond. When the fog rolled in and visibility dropped to nothing, the foxhole became the entire universe, a small, manageable universe that could be controlled and understood. On the other hand, the space was confining in ways that could become oppressive. There was no standing up straight, no stretching fully, no privacy. Every movement had to be calculated. Reaching for equipment meant carefully shifting position to avoid knocking into walls or kicking your partner. Going to the bathroom meant climbing out of the hole, exposing yourself to the elements and to potential enemy observation, then climbing back in. The sensory environment within this space was distinct. The earth itself provided some insulation from sound, muffling the distant noises of the war into a low continuous rumble. But sounds within the hole were amplified. The breathing of your partner, the rustle of fabric, the click of metal on metal as you adjusted your weapon. These sounds became the soundtrack of foxhole life. Temperature varied within the hole in ways that were not immediately obvious. The floor was always the coldest part, conducting heat away from any surface in contact with it. The walls were slightly warmer, but still cold enough to chill any body part pressed against them. The air near the top of the hole, just below ground level, was the warmest, though still far from comfortable. This created a temperature gradient that soldiers learned to navigate. Sitting up meant being slightly warmer, lying down meant being colder, but also being below the level where wind could reach. Light was another consideration. During the day, a foxhole received some ambient light, enough to see inside the space without artificial illumination. But at night, the hole became absolutely dark unless the soldier risked using a light source. This darkness was complete and disorienting. Soldiers learned to navigate their small space by touch and memory, knowing exactly where each item was positioned, so they could find it without sight. The air quality in a covered foxhole could become poor. When logs and dirt were placed over the top for protection from artillery, the space became partially sealed. Breathing consumed oxygen and produced carbon dioxide. If a heating source was used, it consumed oxygen as well and produced various gases depending on the fuel. Soldiers learned to ensure some ventilation remained, usually a small gap at one end of the cover, to allow fresh air to circulate. Moisture was a constant presence. The warmth of 2 human bodies, their breath, their perspiration, all of this added water vapour to the air inside the foxhole. In the cold environment, this vapour would condense on any surface cooler than the dew point. The walls would become damp. Any metal objects would develop a film of water. Fabric would absorb moisture from the air. This condensation was unavoidable, but it had to be managed. A wet foxhole was a cold foxhole, and a cold foxhole was a dangerous place to try to sleep. The dimensions of the space also dictated social interaction. 2 men in an 8x4 area could not avoid each other. There was no retreating to separate areas, no taking time alone. This forced intimacy created bonds quickly. Soldiers who shared a foxhole learned everything about each other: sleeping, habits, fears, hopes, the contents of letters from home. Some of these partnerships lasted only a night before units were reorganised, or casualties required new pairings. Others lasted weeks or months, creating relationships that would endure long after the war ended. But the space demanded cooperation. If one man was restless, the other could not sleep. If one man was sick or injured, the other had to care for him in that confined area. If one man lost his nerve and panicked, the other had to calm him or restrain him. The foxhole was a crucible that tested not just physical endurance, but also the ability to coexist under impossible conditions. This 8x4x4 space was where survival would happen. Everything that followed, the insulation, the heating methods, the watch rotations, would take place within these dimensions. Understanding the space meant understanding the constraints and possibilities of foxhole life. It meant recognizing that comfort was impossible, but survival was achievable if each element was managed carefully. The soldiers did not choose these dimensions. They inherited them from doctrine and from the accumulated experience of previous wars, but they learned to live within them. They learned to make this small volume of Earth into something that could sustain human life through winter nights that seemed designed to extinguish it. The basic hull was complete, but it was not yet safe. A simple rectangular pit offered protection from direct fire, but warfare in winter brought threats from above and from within the hull itself. The soldiers had to modify their subterranean space to address these threats without extensive materials or time. The first modification was the grenade sump. This was a narrow hole dug into the floor of the foxhole, typically in one corner. Its dimensions were smaller than the main excavation, perhaps 8 inches in diameter and 12 to 18 inches deep. The purpose was grimly specific. If an enemy grenade landed in the foxhole, the occupants had only seconds to respond. Throwing it back out was possible in some cases, but in darkness or in a covered hole, this was risky. The grenade might catch on the edge of the hole or on the log cover. It might detonate in mid-throw. The sump offered an alternative. A soldier could kick the grenade into the sump where the force of the blast would be directed upward through the narrow opening rather than outward, into the occupied space of the foxhole. This was not perfect protection. The explosion would still be loud and violent, but the sump directed the primary blast energy away from the soldiers huddled against the far wall. Shrapnel would be partially contained by the earth around the sump. The difference between a grenade detonating in open space and one detonating in a sump could mean the difference between minor wounds and fatal ones. Digging the sump was challenging work in frozen ground. It required the same chipping and prying as the main excavation, but in a much more confined space. Soldiers used the pointed end of their entrenching tool or sometimes a bayonet to break up the frozen earth in the bottom of the narrow shaft. The excavated material was removed by hand, scooped out and dumped at the edge of the foxhole. Despite the difficulty, the sump was considered essential enough that soldiers dug it even when exhausted from creating the main hole. The second modification addressed a different problem: water. The floor of a foxhole was the lowest point in the immediate area. Any water that entered the hole, from rain, snowmelt, or groundwater seepage, would accumulate there. Standing or lying in water was dangerous. Wet clothing lost its insulating properties. Wet feet were the first step toward trench foot, a debilitating condition that could remove a soldier from combat for weeks or months. To address this, soldiers created a sleeping shelf. This was a raised platform carved into one wall of the foxhole, approximately 12 to 18 inches above the floor. It was not a complex structure, simply a ledge of earth left in place during excavation, wide enough for a man to lie on. If the ground was too frozen to carve this ledge effectively, soldiers would build up a platform using logs, branches, or any other materials they could gather. The sleeping shelf served multiple purposes. It kept the soldier's body above any water that accumulated in the bottom of the hole. It provided a slightly warmer position, as cold air settled to the floor while the shelf remained in the marginally warmer middle zone of the foxhole, and it created two distinct levels within the space, allowing one soldier to sleep on the shelf while the other sat on the floor for watch duty. The shelf had to be wide enough to accommodate a sleeping man without the risk of rolling off during the night. Approximately 2 feet was typical, though this varied based on the soil conditions and the amount of time available for construction. The shelf also had to be load-bearing. A soldier in full gear might weigh 200 pounds or more. The earth forming the shelf had to support this weight hour after hour without collapsing. In practice, the shelf often required reinforcement. Soldiers would drive stakes into the back wall and lay branches or small logs across them to create a more stable platform. Pine boughs were particularly useful for this purpose. They were abundant in forested areas. They provided a springy surface that was more comfortable than bare earth, and their scent was preferable to the smell of damp soil. The third major modification was the log cover. This protected against tree bursts, a particularly effective type of artillery round designed to explode in the forest canopy. When these rounds detonated among the branches, they showered the ground below with shell fragments and wooden splinters. Both were equally deadly to men caught in the open or in uncovered holes. Creating a log cover required tools and time. Soldiers used hand axes to cut small trees or large branches. These logs were then laid across the top of the foxhole, spanning the 4-foot width. The logs had to overlap slightly and be thick enough to stop, or at least slow the fragments raining down from above. 6 inches was considered a minimum diameter, though thicker logs were preferred when available. Once the logs were in place, soldiers covered them with earth. This served 2 purposes. It provided additional mass to stop shell fragments, and it camouflaged the position. Fresh logs lying across a hole in the ground were visible from a distance and could draw enemy fire. A layer of dirt made the position blend into the surrounding landscape, especially after snow covered everything with white. The log cover created new problems even as it solved others. It reduced the amount of light entering the foxhole, making the interior darker during the day. It trapped air inside, requiring ventilation gaps to prevent a buildup of carbon dioxide. It made entering and exiting the hole more difficult, as soldiers had to move the logs aside or squeeze through gaps. And it added weight that could collapse if the logs were not positioned properly, or if the earth walls were not stable. Despite these drawbacks, the log cover was essential in areas where artillery fire was frequent. The sound of tree bursts was distinctive, a sharp crack from above followed by a rain of debris hitting the ground and any surfaces below. Soldiers in covered holes would hear this deadly rain striking the logs overhead and know that they had just been spared from wounds or death by those few inches of wood and dirt. Not all foxholes received all these modifications. Time, energy, and tactical situation determined what was possible. A position that would only be occupied for a single night might receive only the most basic excavation. A position that would be home for a week might be developed with all 3 modifications plus additional refinements. But soldiers understood that each modification increased their chances of surviving not just the enemy, but also the random violence of modern artillery warfare. The engineering was simple, but it was not primitive. Each modification represented an understanding of threat and a practical response to that threat. The grenade sump was applied physics, redirecting blast energy away from vulnerable human bodies. The sleeping shelf was applied thermodynamics, raising the body above the coldest zone and the accumulated water. The log cover was applied ballistics, interposing mass between falling fragments and flesh. These modifications transformed the hole from a simple excavation into a fighting position and a living space. They represented hours of additional labour beyond the initial digging, labour performed by men who were already exhausted, cold and often hungry. But they did this work because they understood that the difference between a basic hole and an engineered foxhole could be measured in survival rates. With these modifications complete, the soldiers had created the best shelter possible under the circumstances. It was not warm, not comfortable, not anything like a home in the conventional sense, but it was below ground level. It had protection from grenades, water and tree bursts. It had a raised platform for sleeping. It was, within the constraints of the winter warfare, as safe as it was possible to be. Now came the next challenge, staying warm enough to survive the night. The human body is a heat engine. At rest, it generates approximately 100 watts of thermal energy, roughly equivalent to a bright incandescent light bulb. This heat is produced as a byproduct of the chemical reactions that sustain life. The heart pumps blood, the lungs process oxygen, the brain sends signals, and all of this activity produces warmth. In normal conditions, the body regulates its temperature through a balance of heat generation and heat loss. When it becomes too warm, blood vessels near the skin dilate to release heat. Sweat evaporates from the surface, cooling the body through evaporation. When it becomes too cold, blood vessels constrict to preserve heat in the core, and muscles begin to shiver to generate additional warmth through motion. But these mechanisms have limits. When the environment is cold enough, when the body is wet, when energy reserves are depleted, the system begins to fail. Core temperature starts to drop. This is hypothermia, and it progresses in stages that move from uncomfortable to dangerous to fatal. In a winter foxhole, all the conditions for rapid heat loss were present. The soldier was surrounded by frozen earth, which conducted heat away from any surface in contact with it. Cold air filled the space, drawing warmth from exposed skin. Damp clothing from snow, rain, or condensation accelerated the cooling process, and the soldier was trying to rest, which meant reducing the physical activity that would generate additional body heat. Heat leaves the body through 4 primary mechanisms. Understanding these was essential to surviving winter nights, even if soldiers did not use technical terms to describe them. Conduction is heat transfer through direct contact. When a soldier lay on frozen ground, heat flowed from his body into the earth. The ground was an enormous heat sink, capable of absorbing vast amounts of thermal energy without its temperature changing noticeably. No amount of body heat could warm frozen earth. It simply drained warmth continuously, degree by degree. This was why insulation was critical. Any material that prevented direct contact between body and ground slowed the rate of heat loss. Pine boughs, straw, spare clothing, even a layer of dry leaves, all of these created a barrier that reduced conduction. The material did not have to be warm. It simply had to be a poor conductor of heat, allowing the soldier's body heat to remain in his body rather than flowing into the earth. Convection is heat transfer through moving air or liquid. Cold air touching warm skin absorbs heat and then moves away, carrying that heat with it. New cold air takes its place, and the cycle continues. This is why wind makes cold feel colder. It accelerates convective heat loss by constantly replacing the thin layer of warmed air around the body with fresh cold air. In a foxhole, convection was somewhat reduced compared to open ground. The earth walls blocked wind to some degree, but air still moved through the space, especially in uncovered holes or holes with gaps in the log cover. This air circulation was necessary to prevent carbon dioxide buildup, but it also meant continuous heat loss through convection. The solution was layering, multiple layers of clothing trap air between them. This trapped air is warmed by the body but cannot easily move away, reducing convective heat loss. Wool was particularly effective for this purpose. Its fibre structure naturally trapped air, and unlike cotton or some other materials, wool retained its insulating properties even when damp. Radiation is heat transfer through electromagnetic waves. All objects above absolute zero emit infrared radiation, and warm objects emit more than cold objects. A soldier's body radiated heat continuously into the cooler environment around him. This heat loss occurred even without direct contact or moving air. It happened across empty space. Reducing radiative heat loss required reflecting or blocking the infrared radiation. In practical terms, this meant covering the body with materials that were either reflective or had their own thermal mass. A wool blanket absorbed the infrared radiation and warmed slightly, reducing the gradient between body and environment. This slowed the rate of heat loss but could not stop it entirely. Evaporation is heat loss through the phase change of water from liquid to gas. When sweat evaporates from skin, it carries away heat. This is an efficient cooling mechanism when the body's too warm, but in a cold environment it becomes a dangerous source of heat loss. Wet clothing was particularly problematic. Water evaporating from fabric removed heat not just from the fabric, but from the skin beneath it. Soldiers learned to avoid sweating when possible by regulating their activity level. They learned to remove wet clothing as soon as practical and to dry it using any heat source available. And they learned that staying dry was almost as important as staying warm, because wet cold was far more dangerous than dry cold. These 4 mechanisms worked simultaneously. A soldier lying in a foxhole was losing heat through conduction to the ground, convection to the air, radiation to the surrounding earth walls, and evaporation from any damp clothing or exposed skin. The combined rate of heat loss could easily exceed the body's ability to generate replacement heat, especially when the soldier was at rest and when food intake was limited. The rate of heat loss increased dramatically with decreasing temperature. At 10 degrees Fahrenheit, with wet clothing and direct contact with frozen ground, an unprotected soldier could develop severe hypothermia within a few hours. At 60 below zero, the time frame shortened to perhaps 30 minutes before the body began to lose its ability to maintain core temperature. This was the fundamental challenge. The soldier needed to sleep, which meant remaining still for extended periods. But remaining still in these conditions meant cooling to dangerous levels. The solution required multiple interventions working together. Insulation to reduce conduction, layering to reduce convection, coverings to reduce radiation, and dryness to eliminate evaporation. But these passive measures alone were often insufficient. When the external temperature was cold enough, when the soldier had been exposed long enough, when his energy reserves were depleted from days or weeks of inadequate food and continuous stress, passive insulation reached its limits. This is where active heating became necessary. The soldiers needed external sources of warmth to supplement their body's failing heat production. But generating heat in a foxhole brought its own set of challenges. Open flames were visible to enemy observers. Smoke could be detected from hundreds of yards away. The smell of burning wood or fuel could give away a position. And the soldiers had limited materials available for fuel. What emerged was a collection of heating methods that balanced warmth against safety. These methods were taught through official channels in some cases and developed through soldier ingenuity in others. They range from military-issued fuel tablets to improvised devices constructed from scavenged materials. They were quiet, they were mostly smokeless, and they provided just enough heat to keep a soldier alive through the night without revealing his position to enemy guns. The problem of heat loss was not solved but managed. Through insulation, through careful material selection, through controlled heating, and through the shared warmth of partnership, soldiers found ways to maintain their core temperature through winter nights that seemed designed to extinguish life. It was a fragile balance, constantly threatened by wind, moisture, exhaustion, and hunger. But it was a balance that could be maintained with knowledge, discipline, and the small technologies that we will explore in the chapters ahead. The forest floor provided many materials for insulation, but one of the most effective was often overlooked in accounts of winter warfare. Straw, when available, offered thermal properties that surpassed even standard-issue wool blankets under certain conditions. Straw is not simply dried grass. Its structure is specific and purposeful. Each stalk is hollow, a tube of plant matter with air trapped inside. This air cannot move freely, cannot convect away heat. When many stalks are bundled together, they create thousands of these tiny air pockets, each one acting as a miniature insulation chamber. The principle is the same as modern insulation materials. Trap air in small spaces and heat transfer slows dramatically. But the soldiers in winter foxholes did not need to understand the physics in technical terms. They simply needed to know that a layer of straw between their body and the frozen ground made the difference between bearable cold and dangerous cold. Straw was not always available. In heavily forested areas, it might be absent entirely. But near farmland, near barns or storage structures, soldiers could sometimes find it. A bundle of straw carried back to a foxhole became a valuable commodity, worth the effort of transport despite its bulk. The application was straightforward. Straw was scattered across the floor of the foxhole, creating a layer several inches thick. This layer provided immediate separation from the frozen earth. The individual stalks compressed somewhat under body weight, but not completely. Even compressed straw retained enough air pockets to reduce conductive heat loss significantly. The thickness of the layer mattered. A thin scattering of straw provided minimal benefit. 3 to 4 inches was more effective. 6 inches was better still, though this required substantial quantities of material. Soldiers learned to prioritise thickness over coverage area. A thick layer under the torso and hips was more valuable than a thin layer covering the entire floor. Straw had another advantage over some other insulating materials. It resisted moisture to some degree. The waxy surface of the stalks did not readily absorb water. When moisture did accumulate in a straw layer, it could be shaken out more easily than from fabric or wood. This maintenance was important, because wet insulation was worse than no insulation. It conducted heat away from the body while providing no thermal barrier. The soldiers developed a routine for managing straw. During the day, if weather permitted, the straw would be removed from the foxhole and spread in sunlight to dry. Even weak winter sun could evaporate surface moisture over a few hours. The dried straw would then be returned to the foxhole before nightfall, ready to provide its insulating function through another cold night. In some cases, soldiers created modular panels. They would gather straw and compress it between 2 pieces of fabric or between rough wooden frames if materials allowed. These panels could be placed on the floor or even hung against the walls of the foxhole. The advantage of panels was ease of handling. They could be quickly removed for drying or moved aside during the day when insulation was less critical. The concept of modular straw panels paralleled techniques used in other contexts. Japanese gardeners wrapped straw around trees in a method called komomaki, providing winter protection and a warm refuge for insects. The principle was identical: straw as a thermal buffer, shaped and positioned for specific protective purposes. Straw also provided cushioning beyond its thermal properties. The floor of a foxhole, even when dry, was hard and uneven. Hours of lying on frozen earth led to pressure points, soreness, and difficulty sleeping, even when warmth was adequate. Straw created a softer surface, more forgiving to hips and shoulders. This comfort factor, while secondary to survival, still mattered for soldiers who needed to rest effectively during their off-watch hours. The smell of straw in a foxhole was distinct. It carried associations of farms and harvests, of autumn and stored grain. In the midst of mud and cordite and unwashed bodies, this scent provided a small sensory link to civilian life, to a world that continued to exist beyond the front lines. Whether this was comforting or painful depended on the individual soldier and his state of mind. There were practical considerations for straw use. It was flammable, which meant any heating source had to be positioned carefully away from the straw layer. A stray spark from a cigarette or a heating tablet could ignite dry straw quickly, creating a dangerous fire in the confined space of a foxhole. Soldiers learned to create designated areas for heat sources, bare patches of earth where no straw was present. Straw also provided habitat for insects and rodents, though this was less of a concern in winter when most such creatures were dormant or had moved to deeper shelter. Still, soldiers sometimes found that their straw layer was not entirely unoccupied. Small mice or beetles might be discovered burrowed into the insulation. Most soldiers tolerated this. The creatures were harmless and in some small way provided company in the isolation of the foxhole. The logistics of straw acquisition varied by location and circumstances. Near agricultural areas, abandoned barns or storage sheds might yield substantial quantities. Farmers fleeing the war zone sometimes left behind hay and straw stores. In other cases, soldiers might trade with local civilians, offering rations or other goods in exchange for insulation materials. When straw was unavailable, soldiers substituted other materials with similar properties. Dry grass, when gathered in sufficient quantity and kept dry, provided comparable insulation. Dead leaves worked but compressed more readily and retained moisture more easily. Pine needles were less effective but better than nothing. The principle remained the same: create an air-trapping layer between body and frozen ground. The effectiveness of straw insulation could be quantified, though soldiers did not carry thermometers or calculate our values. They simply knew that nights spent on straw were survivable in ways that nights spent on bare ground were not. Body temperature remained stable longer. Shivering was less constant. Sleep, when it came, was deeper and more restorative. There is a simple test that soldiers learned through experience. If you could lie on your insulation layer for 10 minutes without feeling the cold penetrating from below, the insulation was adequate. If cold seeped through within 5 minutes, more material was needed. This practical assessment required no instruments, only attention to the body's signals. The value of straw was forgotten in the sense that military training manuals did not emphasize it. Official doctrine focused on issued equipment, blankets, sleeping bags, shelter halves. But field experience taught that improvised materials were often more available and sometimes more effective than what the supply system provided. Straw became part of the informal knowledge passed from veteran soldiers to new arrivals. In the hierarchy of survival priorities, securing adequate floor insulation ranked high. Before a soldier worried about heating sources or elaborate shelter construction, he needed to solve the problem of ground contact. Straw, when available, solved this problem simply and effectively. It asked only that the soldier gather it, transport it, maintain its dryness, and position it correctly. The nights when straw was available were noticeably different from nights without it. The cold was still present, still dangerous, but it was no longer absolute. The soldier lying on his straw layer could feel his body heat staying with him, rather than draining away into the earth. This small victory, heat retained rather than lost, made survival possible, and survival, repeated night after night, was how soldiers endured the winter that seemed determined to kill them through temperature alone. The forest, despite its role as battleground, provided resources. Trees that had stood for decades or centuries now offered their branches to soldiers who needed any advantage against the cold. Pine boughs, the small branches bearing needles, became one of the most widely used natural insulation materials on the winter front. Pine trees were common in many areas where winter fighting occurred. The Ardennes forest held substantial pine populations. The forests of Eastern Europe contained vast expanses of coniferous growth. These trees remained green through winter, their needles still attached to branches even as deciduous trees stood bare. Harvesting pine boughs required only a hand axe or a knife. Soldiers would select branches from the lower parts of trees, where they could be reached without climbing. A cut through the base of the branch would separate it from the trunk. Several such cuts would yield an armload of boughs, enough to begin insulating a foxhole. The branches varied in size. Some were thin and flexible, bearing only a sparse covering of needles. Others were thick and densely covered, heavy with foliage. Soldiers learned to select for density. More needles meant more air trapped between them, which meant better insulation. The length of the branch mattered, less than its coverage. Once gathered, the boughs were arranged in the foxhole. The most common application was layering them on the floor, creating a springy mat between the soldier and the frozen earth. The branches were placed with needles pointing upward, so that lying on them meant being supported by the flexible stems rather than lying directly on the rigid wood. This arrangement created multiple layers of trapped air. The space beneath the branches held air warmed slightly by the earth below. The needles themselves trapped air between their narrow blades, and the gap between the top of the boughs and the soldier's body held another layer of relatively still air. Each of these layers contributed to reducing heat transfer. The springiness of pine boughs was a significant advantage. Unlike straw, which compressed into a relatively flat layer, pine branches maintained their three-dimensional structure under body weight. This created a thicker insulation barrier. It also meant that pressure was distributed across many contact points, rather than concentrated on a few, making the sleeping surface more comfortable. Pine boughs also provided traction. The floor of a foxhole could become slippery when wet, frozen mud developing a glaze of ice, or condensation making earth surfaces treacherous. Pine boughs created a textured surface that prevented sliding and made movement within the confined space safer and easier. The scent of pine was strong and persistent. Fresh-cut branches released aromatic compounds, terpenes and other volatile oils that filled the foxhole with a sharp, clean smell. This masked some of the less pleasant odours of unwashed soldiers, damp wool, and stagnant air. The psychological effect was notable. The scent of pine carried associations with holidays, with forests in peacetime, with normalcy. In a small way, This sensory experience provided comfort beyond the physical warmth the boughs delivered. Pine needles shed over time as soldiers moved. On the boughs, as the branches dried and aged, needles would detach and fall to the floor of the foxhole. This created a layer of loose needles beneath the branches, additional insulation, though less structured than the intact boughs. Soldiers would periodically gather these loose needles and add them to the insulation layer or remove them if they became too accumulated and began to create an uneven surface. The branches could also be used for purposes beyond floor insulation. When fashioning a log cover for the foxhole, soldiers would sometimes place pine boughs over the logs before adding the dirt layer. This created additional cushioning and insulation from above. If an artillery shell exploded nearby, the boughs might absorb some of the shock, reducing the force transmitted to the logs and to the soldiers below. In some cases, pine boughs were woven together or tied with cord to create more stable mats. This required additional time and materials but produced a more durable product that could be moved as a unit, lifted out for drying, repositioned for maintenance, or carried to a new foxhole if the unit relocated. These woven mats represented a step toward more sophisticated field engineering, though most soldiers simply used loose boughs arranged in overlapping layers. The durability of pine boughs varied with weather conditions. In dry cold, the branches remained flexible and functional for many days. In wet conditions, they would absorb moisture, become heavier, and begin to lose their spring. Eventually, after a week or more of use, the boughs would need to be replaced as they became compressed, brittle, or decomposed. Replacing the boughs meant another trip to gather fresh branches. This was not always possible. Combat conditions, enemy observation, or simple exhaustion might prevent a soldier from leaving his foxhole during daylight. In these cases, the existing boughs were used until they became completely ineffective, at which point the soldier would resort to whatever other materials were available or accept the greater discomfort of less adequate insulation. The colour of fresh pine boughs was a deep green, a stark contrast to the whites and greys of the winter landscape and the brown of frozen earth. This meant that boughs visible from outside the foxhole could compromise camouflage. Soldiers learned to cover any visible pine with dirt or snow, ensuring that the position blended into its surroundings. Inside the foxhole, where visibility from outside was not an issue, the green colour was welcome, a reminder that life persisted even in winter. Pine boughs froze when temperatures dropped low enough. The moisture within the needles and branches would crystallise, making the material rigid and less comfortable. But even frozen, the boughs still provided insulation. The structure remained, the air pockets remained, and heat transfer was still reduced compared to direct contact with earth. Frozen boughs were simply less pleasant to lie on, their surfaces hard and unyielding. Some soldiers developed preferences for certain types of pine. White pine, with its soft, flexible needles, was considered more comfortable. Red pine, with stiffer needles, was less preferred, but still functional. Spruce and fir, which are not technically pines but were often grouped with them by soldiers, also provided adequate boughs. The differences were minor enough that most soldiers used whatever was available, rather than searching for a preferred species. The military supply system did not provide pine boughs. They were not part of official equipment lists, not mentioned in training manuals, not distributed through quartermaster channels, yet they became as standard a part of foxhole life as the entrenching tool or the rifle. This was improvisation born of necessity, a solution developed by soldiers who needed insulation and found it growing in the forest around them. The act of gathering pine boughs was itself a brief escape from the foxhole. Even in dangerous conditions, even when enemy fire was a constant threat, the few minutes spent cutting branches provided a change of environment and activity. Movement warmed the body. The forest, despite hosting combat, still offered moments of relative peace. The quiet of trees, the crunch of snow underfoot, the simple task of cutting and gathering. Pine boughs represented a connection to the natural world in the midst of industrial warfare. Artillery and aircraft and chemical explosives were human inventions, products of factories and laboratories. But pine trees had existed long before the war and would exist long after. Using their branches for warmth was a reminder that survival often depended more on understanding natural materials than on advanced technology. The effectiveness of pine bough insulation could be measured in the same practical way as straw. Did it prevent the cold of the ground from penetrating quickly? Soldiers lying on a proper layer of boughs would feel supported, would feel the springiness of the branches, and would notice that the bone-deep chill of frozen earth took longer to reach them. This delayed onset of ground cold was enough to make sleep possible, enough to prevent hypothermia during the hours of rest. In combination with other insulation materials, straw on the floor, pine boughs on top of the straw, a blanket or sleeping bag on top of the boughs, soldiers could create a layered system that provided substantial protection from conductive heat loss. Each material contributed its particular properties: straw for trapped air, pine for structure and additional air pockets, fabric for direct contact with skin, and reduction of convective loss. The simplicity of pine bough use made it accessible to every soldier. No special training was required, no complex tools, no rare materials. A hand axe, a nearby pine tree, and a few minutes of work produced a functional insulation layer. This simplicity meant that even soldiers, arriving at a new position in darkness, could quickly improve their sleeping conditions by gathering whatever boughs were within reach. The pine boughs in a foxhole were not permanent. They were replaced, moved, adjusted, discarded, and replenished as needed. But during the nights when they served their purpose, they made survival possible. They were one more element in the collection of small solutions that allowed soldiers to endure winter conditions that would have been fatal without constant adaptation and improvisation. Darkness was both protection and prison. During the long winter nights, when visibility collapsed and combat slowed, soldiers might have welcomed the opportunity to light a fire, to warm themselves with open flame and bright light. But this was impossible. Any visible light could mean death. The battlefield at night operated under strict principles. Light revealed position. Position invited fire. Fire caused casualties. This simple chain of cause and effect meant that soldiers lived in darkness, accepting cold and discomfort rather than risking the alternative. Enemy observers watched the front lines constantly. During the day, they noted landmarks, estimated distances, and prepared firing data. At night, they watched for any sign of activity. A struck match could be seen from hundreds of yards away. The glow of a cigarette was visible at similar distances. A small cooking fire would draw attention immediately. Once a position was located by light signature, enemy artillery could be directed to that spot. The time from observation to incoming shells might be only minutes. A soldier who lit a cigarette might not survive to finish smoking it. This was not hypothetical. It happened regularly enough that light discipline became one of the most strictly enforced rules of frontline existence. The same principle applied to smoke. Wood smoke has a distinctive smell that carries for great distances, particularly in the cold, still air of winter. Nights, an enemy soldier downwind of a wood fire might smell it long before seeing any flame. This smell provided intelligence, location of enemy positions, approximate number of soldiers based on fire size, and confirmation that the position was currently occupied. Smoke was also visible during the day. A plume rising from a foxhole or a trench line marked that position clearly. Even in fog or snow, smoke could be detected against the white background. Aircraft observers, enemy scouts, and artillery spotters all watched for smoke as an indicator of where to concentrate their attention and their fire. The result was that soldiers could not use traditional heating methods, no campfires, no wood stoves, no burning of debris or furniture from destroyed buildings. These heat sources, which would have provided substantial warmth and the ability to cook hot meals, were simply too dangerous to employ in forward positions. This created a difficult problem. The soldiers needed heat to survive, winter nights, but they could not produce heat in ways that revealed their location. The solution required different approaches, different technologies, different fuels that burned without the signatures of traditional fire. The military supply system recognized this problem and provided partial solutions. Specialized fuel tablets were developed and issued specifically for use in field conditions, where light and smoke discipline were essential. These tablets represented careful engineering, fuels chosen and refined to burn with minimal visible flame and minimal smoke production. The soldiers' acceptance of darkness was nearly total. Foxholes at night were black spaces where vision provided almost no information. Soldiers navigated by touch and memory. They learned the position of every item in their small space, where the ammunition was stored, where the rations were kept, where their partner slept. All of this knowledge had to exist without visual confirmation. Communication between foxholes at night was also constrained. Voices carried, so talking was kept to whispers or avoided entirely. Hand signals were useless in darkness. Movement between positions was dangerous. A soldier crawling from one hole to another risked being shot by his own side, as nervous sentries might fire at any movement they detected. This isolation added to the psychological burden. Each foxhole became its own universe through the night hours, cut off from other positions by darkness and silence. The knowledge that other soldiers were nearby, perhaps only 20 or 30 yards away, provided little comfort when no communication or contact was possible. The discipline extended to seemingly minor sources of light. Wristwatches with luminous dials had to be kept covered. Map reading required a soldier to create a tent with his blanket or coat, then use a carefully shielded flashlight for only the minimum time necessary to check the map. Even the momentary opening of a hooded lantern required careful consideration of whether the risk was justified. Some soldiers developed techniques for creating minimal light. A match might be lit inside a deep can or box, visible only to the person using it and not detectable from outside. A candle might be placed at the bottom of a covered foxhole, where its glow could not reach above ground level. These methods were not perfect. Some light always escaped, but they reduced the risk compared to open flames. The tyranny of light discipline meant that certain activities became nearly impossible. Reading letters from home required waiting for daylight or taking significant risks. Writing responses was similarly constrained. These activities, which provided important psychological support, were difficult to accomplish in the hours when soldiers had time available. Maintenance of equipment in darkness was challenging. Cleaning a weapon required disassembly, which meant keeping track of small parts without being able to see them. Loading ammunition into magazines, checking gear for damage, or making repairs to clothing, all of these tasks were complicated by the absence of light. The human eye adapts to darkness over time, developing increased sensitivity as the pupils dilate and chemical changes occur in the retina. This adaptation requires approximately 30 minutes of darkness to become fully effective. Any exposure to bright light resets this process, destroying the night vision that had developed. Soldiers learned to protect their night vision carefully. If light was absolutely necessary, they would close one eye before exposure, preserving the dark adaptation in that eye. This meant they could return to effective night vision more quickly after the light was removed. This technique was standard training but required conscious discipline to implement consistently. The absence of light also affected circadian rhythms. Humans are adapted to cycles of light and dark, using these cues to regulate sleep patterns and alertness. In a foxhole, where darkness was enforced for security rather than natural cycles, these cues were disrupted. Soldiers might be awake during the actual night hours, then trying to sleep during daylight when their bodies expected to be active. The moon became important in ways that soldiers in civilian life rarely considered. A full moon provided significant illumination, enough to see terrain features, to navigate between positions, to conduct limited activities without artificial light. But this same illumination also made movement more visible to enemy observers, increasing danger. Moonless nights were darker but safer for any necessary movement. Cloud cover affected visibility in complex ways. Heavy clouds blocked moonlight but also trapped thermal radiation from the ground, making nights slightly warmer. Clear skies allowed more moonlight but also permitted heat to radiate into space, making nights colder. Soldiers learned to recognize these patterns, adjusting their preparations based on the evening sky. The psychological impact of enforced darkness was significant. Humans find comfort in light, associate it with safety and civilization. Darkness carries associations with danger and the unknown. Living in darkness for hours each night, unable to produce light even when cold and frightened, required mental adaptation. Some soldiers adjusted easily. Others struggled with the constant darkness, finding it oppressive beyond the physical discomfort it caused. This was the context in which soldiers had to find warmth They needed heat sources that operated in total darkness or near darkness. They needed fuels that burned without smoke or with minimal smoke. They needed methods that provided warmth without betraying their position to an enemy actively searching for targets. What emerged was a collection of heating techniques that respected the tyranny of light discipline. These methods were constrained, limited in the heat they could provide, often insufficient for true comfort. But they operated within the narrow parameters that survival required. They kept soldiers alive without making them targets, and in doing so, they represented some of the most careful engineering and improvisation of the entire war. The tablet was small, weighing only a few ounces. White or slightly yellow in colour, it had a waxy texture and a faint chemical smell. This was hexamine, a solid fuel developed specifically for military use, and it solved many of the problems that traditional fuels created on the battlefield. Hexamine had been invented in the 1930s, a product of chemical research into stable portable fuels. Its full chemical name was hexamethylentetramine, but soldiers knew it simply as heat tabs or fuel tablets. The tablets were issued in small tins, each containing enough fuel for several uses. These tins fit easily into a pack or pocket, taking up minimal space and weight. The critical property of hexamine was how it burned. When ignited, it produced a flame that was almost invisible in daylight, and appeared as a pale blue glow in darkness. This flame was small, steady, and produced minimal smoke. For soldiers who needed heat but could not afford to reveal their position, these properties made hexamine invaluable. The energy density of hexamine was substantial, approximately 30 megajoules per kilogram. This meant that a small tablet could produce significant heat relative to its size. A single tablet weighing 14 grams could burn for approximately 10 to 12 minutes, providing enough heat to warm a canteen cup of water or to provide radiant warmth to hands held above the flame. Using hexamine required a small stove or platform. The military issued compact folding stoves designed specifically for these tablets. The stove was typically made of pressed steel, with a base to hold the tablet and a top platform to support a canteen cup or small pot. Folding arms allowed the stove to collapse flat for transport. The soldier would unfold the stove and place it on level ground, away from any flammable materials. A hexamine tablet was removed from its tin and positioned in the centre of the stove base. Ignition was accomplished with a match or lighter. The tablet would begin to melt slightly as it burned, creating a small pool of liquefied fuel that sustained the flame. Once ignited, the hexamine flame required no tending. It burned steadily at a consistent rate until the tablet was consumed. There was no need to add fuel, adjust airflow, or otherwise manage the fire. The soldier could place water onto heat and then attend to other tasks, checking occasionally to see when the water reached the desired temperature. The blue flame was hot enough for practical purposes. Water could be brought to a boil, though this took longer than with a wood fire or a gasoline stove. More commonly, soldiers heated water to a temperature suitable for tea or coffee, hot enough to warm from the inside but not necessarily boiling. The warmth of a hot drink was psychological as much as physical, providing comfort and a sense of normalcy. The smoke production of hexamine was minimal, but not zero. The flame produced some visible vapour, particularly in cold air where any warm gas became visible as condensation. This meant that hexamine use still required some caution. In a covered foxhole with limited ventilation, the small amount of smoke would dissipate slowly. In open positions very close to enemy lines, even the minimal smoke might be noticeable. The smell of burning hexamine was distinctive, slightly fishy or chemical. This smell was noticeable to anyone nearby but did not carry as far as wood smoke. In the complex odour environment of the front lines, where cordite, mud, unwashed soldiers, and diesel fumes all mixed together, the hexamine smell was one more component rather than a distinctive signature. The flame produced carbon dioxide, water vapour, and trace, amounts of other combustion products including formaldehyde and nitrogen oxides. In open air, these dispersed harmlessly. In a confined, poorly ventilated space, they could accumulate to uncomfortable or even dangerous levels. Military instruction sheets for hexamine use specifically warned about ensuring adequate ventilation, particularly in covered dugouts or bunkers. The heat output of a single hexamine tablet was modest. It could warm hands held above it for a few minutes. It could heat a small quantity of water or food, but it could not heat the interior of a foxhole to a comfortable temperature. For that, multiple tablets burning simultaneously would have been required, which would have used up the limited supply quickly and produced more smoke and smell than was safe. Despite these limitations, hexamine provided critical capability. The ability to heat water for a hot drink in winter conditions was significant for morale and for basic physiological function. A hot beverage raised core body temperature temporarily, provided hydration, and delivered calories if the drink contained sugar or other nutrients. The psychological benefit of holding a warm cup and drinking something hot was considerable. Hexamine also enabled heating of rations. Many military rations were designed to be eaten cold if necessary, but they were more palatable when warmed. A canteen cup of stew or soup, heated over a hexamine flame, became a more satisfying meal than the same food eaten cold from the can. This improved calorie intake, as soldiers were more willing to eat adequate amounts of warmed food compared to cold rations. The tablets were reasonably weather-resistant. They could get wet without being destroyed, though wet tablets were more difficult to ignite. Soldiers learned to keep their hexamine tins sealed and stored in relatively dry locations. A tin that had been opened and exposed to moisture for extended periods might contain tablets that had begun to degrade or that refused to light reliably. The supply of hexamine varied by unit and by timing. Some soldiers received regular resupply and had adequate tablets available. Others went through long periods with few or no tablets, having to rely entirely on improvised heating methods. The tablets became a trade commodity. Soldiers with extra hexamine might exchange it for cigarettes, food, or other valued items. There were also national variations in fuel tablet design. German forces used Esbit tablets, which were similar to hexamine in function, but with slightly different chemical composition. British forces had their Tommy Cooker tablets. American forces used various formulations. All served the same basic purpose, providing portable, relatively smokeless heat for field cooking. The hexamine flame was sometimes used for purposes beyond heating food and water. Soldiers would use it to warm their hands briefly before going on watch, restoring some dexterity to cold, stiffened fingers. It could be used to thaw frozen equipment. A rifle bolt frozen shut might be carefully warmed to restore function. Water frozen in canteens could be thawed, though this had to be done carefully to avoid cracking the canteen. In the hierarchy of heating solutions, hexamine occupied an important position. It was official, issued through supply channels, designed specifically for military field use. It provided heat with minimal risk of detection, but it was also limited in supply and modest in heat output. For soldiers who needed more warmth than hexamine alone could provide, or who found themselves without hexamine tablets, other solutions had to be found. The blue flame of hexamine represented military engineering applied to a specific problem: how to let soldiers heat food and water in conditions where traditional fire was impossible. The solution was not perfect. The heat was modest, the supply often inadequate, and the tablets could not warm a foxhole or provide heat through an entire night. But within its design parameters, hexamine functioned well. It gave soldiers one reliable tool in their collection of survival methods, one small source of warmth in a winter that offered very little. The British Army issued a heating device that soldiers called the Tommy Cooker. It was a small tin, roughly the size of a shoe polish container, containing solidified methylated spirits. This was fuel alcohol, ethanol that had been denatured with methanol and other additives to make it undrinkable, then mixed with a gelling agent to transform it from liquid to solid. The tin itself was simple stamped metal with a lid that could be pried off. Inside, the solidified fuel appeared as a waxy or gel-like substance, pale in colour. The entire unit weighed only a few ounces and could be carried easily in a pack or pocket. Like hexamine, it was designed for portability and ease of use in field conditions. To use the Tommy Cooker, a soldier would remove the lid and place the open tin on a stable surface. The fuel did not need to be removed from the container, it burned directly in the tin. Ignition was accomplished with a match, and once lit, the surface of the fuel would burn with a steady flame. The flame from methylated spirits was similarly low visibility compared to wood fires. It burned with a slight yellow-blue colour, producing minimal smoke. The heat output was comparable to hexamine. sufficient for heating a canteen cup of water or warming a small quantity of food. The fuel would burn for 10 to 15 minutes depending on the size of the tin and the amount of fuel it contained. One advantage of the Tommy cooker design was wind resistance. Because the fuel burned inside its container, the flame was somewhat protected from drafts and breezes. This made it more reliable in outdoor conditions where wind might blow out a less protected flame. In the trenches and foxholes of winter warfare, where wind was a constant presence, this reliability was valuable. The solidified fuel also addressed a safety concern. Liquid alcohol is dangerous in combat conditions. A container might rupture, spilling flammable liquid that could ignite catastrophically. Solidified fuel eliminated this risk. Even if a tin was damaged or punctured, the gel-like substance would not pour out. It might burn if ignited, but it would burn in place rather than spreading. The fuel could be extinguished by replacing the lid on the tin, cutting off the oxygen supply. This meant that a soldier could use part of a tin, then save the remainder for later. This flexibility extended the usefulness of each issued unit. A single Tommy cooker tin might provide heat for several sessions of warming water or food rather than being consumed all at once. The damp climate of European winters was particularly challenging for heating devices. Many fuels absorbed moisture from the air, degrading their performance or becoming impossible to ignite. The solidified methylated spirits in a Tommy cooker tin were less susceptible to moisture damage when stored in their sealed container. Even in very humid conditions, the fuel remained functional as long as the seal was intact. The smell of burning methylated spirits was present but not overwhelming. It carried a slight alcohol odour, somewhat medicinal, different from the chemical smell of hexamine or the organic smell of wood smoke. In the mixed odour environment of the front lines, this smell was noticeable but not dramatically so. It would alert anyone very close to the position that fuel was being burned, but it did not carry the distances that wood smoke travelled. Like hexamine, the Tommy cooker produced combustion products that included carbon dioxide, water vapour, and trace amounts of formaldehyde and other compounds. Ventilation requirements were similar, adequate in open positions, requiring active air circulation in covered spaces. Soldiers learned not to use these devices in tightly sealed dugouts without ensuring fresh air flow. The heat provided by a Tommy cooker was modest in absolute terms. It could not warm the interior of a foxhole to comfortable temperatures. It could not provide enough heat to dry wet clothing significantly. What it could do was heat a drink, warm a meal, and provide a focal point of warmth for a soldier to briefly warm his hands. These capabilities, while limited, were still meaningful in the context of winter survival. The British military's choice to issue solidified methylated spirits rather than solid tablets like hexamine reflected different engineering decisions and available industrial capacity. Both solutions addressed the same problem using different chemistry. Soldiers who had access to both generally found them comparably useful, though individual preferences developed based on minor differences in burn time, heat output, or odour. The Tommy cooker represented what official supply channels could provide, a standardised manufactured solution that partially addressed the heating problem. It was better than nothing, far better than attempting to burn wood and revealing position through smoke. But it was not enough by itself to keep a soldier warm through a winter night. The limitation of all these issued heating devices was their intended purpose. They were designed for cooking, for heating rations and preparing hot drinks. They were not designed as space heaters. The military supply system recognised that soldiers needed to eat and drink in field conditions, so it provided portable cooking fuel. The problem of staying warm during sleep was addressed through issued blankets and sleeping bags, with the assumption that adequate bedding would provide sufficient insulation. This assumption failed in the extreme cold of winter 1944-1945. The bedding provided was often insufficient, particularly when wet. Soldiers needed supplemental heat sources beyond what official channels supplied. This gap between official provision and actual need drove the development of improvised heating methods, devices constructed from scavenged materials using whatever fuel could be found or created. The Tommy cooker, like hexamine tablets, became part of the soldier's toolkit. It was used when available, carefully rationed when supply was limited, and supplemented with improvised alternatives when necessary. The small tins accumulated in foxholes, empty containers that might be reused for other purposes or simply discarded. Some soldiers refilled empty tins with their own improvised fuel mixtures, creating unofficial versions of the Tommy cooker using materials at hand. The very existence of these issued heating devices indicated that military planners understood the need for field heating capability. But the scale of that provision, small tins providing 10 minutes of modest heat, showed that the full scope of the winter survival challenge was not adequately addressed through official channels. Survival required more than what was issued. It required creativity, improvisation, and a willingness to work with whatever materials the battlefield environment provided. When official fuel ran out, soldiers turned to materials that surrounded them. The battlefield was littered with the debris of military operations, empty ration cans, discarded packaging, broken equipment. From this scarcity came innovation. One of the most effective improvised heating devices was the buddy burner, constructed from nothing more than a small can, corrugated cardboard, and wax. The typical construction began with a tuna can or similar low-profile food container. These were abundant. Rations came in cans, and the empty containers accumulated wherever soldiers ate. A can approximately 3 inches in diameter and 1 to 2 inches tall was ideal. The soldier would clean it reasonably well, removing food residue that might produce unpleasant odours when heated. Corrugated cardboard was the second component. Shipping boxes, ration packaging, and other military supplies arrived in cardboard containers. This material was common enough to be considered disposable in normal circumstances, but in a foxhole it became valuable. The soldier would cut strips of cardboard approximately 1 to 2 inches wide and as long as practical. The corrugation was critical. Cardboard consists of 2 flat layers, with a wavy layer sandwiched between them. This wavy layer creates channels running the length of the cardboard. When the cardboard was rolled into a spiral and placed inside the can, these channels stood vertically, creating hundreds of small tubes open at both ends. The rolling process required some care. The cardboard was coiled tightly, starting from one end and wrapping around itself until it filled the can completely. The cardboard should fit snugly, but not be compressed so tightly that the channels collapsed. When properly rolled, the top of the can showed a spiral pattern of cardboard edges with the small hollow channels visible between them. The third component was wax. Candles were sometimes available through official supply or care packages from home. Old candle stubs, pieces of wax from packaging materials, or even paraffin intended for other purposes could serve. The wax needed to be melted and poured into the can filled with rolled cardboard. Melting the wax required a heat source, which presented a circular problem. The soldier needed heat to create a heat source. In practice, this meant using a precious hexamine tablet, or Tommy cooker to melt the wax, or finding a location where a fire could briefly be lit safely away from the front lines. Some soldiers melted wax during daylight hours when smoke might be less noticeable, then poured it into prepared cans for later use. The melted wax was poured slowly into the can, allowing it to soak into the cardboard channels. The cardboard acted like a wick. The wax was absorbed by the paper fibres and drawn into the corrugated spaces by capillary action. If the cardboard was properly rolled, the wax would penetrate throughout, saturating the material. A single tuna can might hold several ounces of wax when fully saturated. Once the wax had cooled and solidified, the buddy burner was complete. It could be stored indefinitely, carried in a pack, and used when needed. The device was simple but represented careful engineering. The cardboard provided structure and acted as a distributed wick. The wax provided fuel. The can contained both and provided a stable base. To use the buddy burner, the soldier would place it on level ground or on a makeshift platform inside the foxhole. Lighting it required only a match touched to the exposed cardboard at the top. The cardboard would catch fire and the flame would begin to melt the wax immediately below it. This melted wax would be drawn into the burning cardboard, sustaining the flame. The burn rate was controllable to some extent. A buddy burner burned from the top down, consuming wax and cardboard together. The flame could be quite substantial, several inches high when first lit, settling to a steady inch or two as the burn established. This flame was larger and brighter than hexamine or methylated spirits, which meant it provided more heat but also more light and smoke. The heat output was significant. A well-constructed buddy burner could boil a pint of water in 8 to 12 minutes. This was comparable to, or faster than, official heating tablets. More importantly, a buddy burner could burn for much longer, 30 minutes to an hour depending on the amount of wax it contained. This extended burn time made it more useful for heating purposes beyond simply warming water. The flame could be extinguished by cutting off oxygen. Soldiers would place a metal cover over the can, another can lid, a piece of metal sheeting, anything flat and non-flammable. Without oxygen, the flame would die within seconds. The wax would resolidify as it cooled, and the buddy burner could be relit later. This ability to stop and restart the device extended its usefulness significantly. The smoke production was moderate. Burning wax and cardboard produced more visible smoke than hexamine or methylated spirits. This meant buddy burners were riskier to use in forward positions where enemy observation was likely. They were more suitable for rear area foxholes, for positions in deep forest where smoke dispersed quickly, or for use during conditions of heavy fog when smoke would not be visible at a distance. The light from a buddy burner flame was also more noticeable. At night, the flame would be visible to anyone with line of sight to the foxhole. This required careful positioning. The burner had to be used in covered foxholes where the log roof prevented the light from being seen from above, or in positions sheltered by terrain features that blocked observation. Despite these limitations, buddy burners became widespread. The materials were universally available, no special tools were required for construction. A soldier could make several burners during a quiet period, storing them for future use. When official fuel ran out, when hexamine tablets were not resupplied, when Tommy Cooker tins were empty, the buddy burner provided an alternative. The device also served purposes beyond heating water. A buddy burner could be used as a space heater in a covered foxhole. The steady flame, burning for 30 minutes or more, would warm the air inside the confined space. This warmth was modest. It might raise the temperature by 5 or 10 degrees, but in extreme cold, every degree mattered. Soldiers learned to enhance the heating effect by creating reflectors. A piece of metal positioned behind the flame would reflect radiant heat toward the soldier. This doubled the effective heat output in one direction, though at the cost of heating the rest of the space less. For a soldier trying to warm himself during his off-watch period, this focused heat was more useful than generalized warming of the entire foxhole. The buddy burner also provided psychological comfort beyond its physical warmth. The visible flame, the sense of having created something functional from scraps, the independence from supply chains, all of this contributed to morale. Soldiers felt less helpless when they could construct their own survival tools rather than depending entirely on what was issued to them. There were variations in buddy burner design. Some soldiers used wider cans for larger burners. Others experimented with different materials, cloth strips instead of cardboard, animal fat instead of wax. Some created burners with multiple wicks by not rolling the cardboard tightly, allowing several independent flames to burn simultaneously. These variations represented individual experimentation and adaptation to available materials. The construction of buddy burners sometimes became a shared activity. Soldiers would work together, one cutting cardboard while another melted wax, creating multiple burners in an assembly line process. This cooperation was practical but also social, a way to spend time during lulls in combat, a task that produced useful results while providing opportunity for conversation and companionship. Empty buddy burners, cans that had burned through their fuel, could be refilled if wax and cardboard remained available. This made them reusable devices rather than single-use items. A soldier might keep the same tin for weeks, refilling it multiple times as materials became available. The can itself would eventually deteriorate from repeated heating, developing cracks or losing its shape, but until then it continued to serve. The buddy burner represented soldier ingenuity at its most practical. It was not a clever trick or a miracle solution. It was simply an effective use of available materials to address a real need. The soldiers who made these devices were not engineers or inventors in any professional sense. They were cold, they needed heat, and they created heat using what they had. This direct problem-solving, born of necessity and executed with whatever resources could be found, characterized much of foxhole life. Among the improvised heating methods developed by soldiers, one technique stood out for its effectiveness despite appearing unlikely at first consideration. An inverted clay flower pot placed over a candle or small burner transformed a point source of heat into a radiant warmer that could change the thermal environment of a foxhole. The basic principle was simple but not obvious. When a candle burns in open air, hot gases rise immediately from the flame. This convection carries the heat upward to the ceiling of the space, where it remains, doing little to warm a soldier sitting or lying near the floor. The candle provides light and minimal radiant heat to anyone near it, but most of its thermal energy is wasted in heating air that then escapes. A clay flower pot changes this, or a pot, dynamic. The pot is placed upside down over the candle, with the drainage hole at the top now serving as a vent. The candle continues to burn, drawing oxygen from the gap at the bottom where the pot does not sit flush against the ground. But now the hot gases rising from the flames strike the inner surface of the pot rather than escaping directly into the room. The clay absorbs this thermal energy. As it heats up, the pot begins to emit infrared radiation, the same type of heat felt when standing near a warm stove or sitting in sunlight. This radiant heat travels outward from the pot in all directions, warming any surface it strikes, including human skin. The advantage of radiant heat over convective heat is significant in a foxhole. Radiant heat does not depend on air movement. It does not rise to the ceiling and disappear. It travels in straight lines from the hot surface to any cooler surface in view, delivering warmth directly to the soldier rather than uselessly warming the air above his head. The clay material itself was important. Clay has specific thermal properties. It absorbs heat relatively slowly, but also releases it slowly. This means the pot acts as thermal mass, storing energy from the candle and continuing to emit heat even after the flame dies. A soldier could light a candle, let the pot heat for 20 or 30 minutes, then extinguish the candle. The pot would continue radiating warmth for another 30 minutes or more as it gradually cooled. The temperature the pot reached depended on several factors: the size of the pot, the intensity of the flame beneath it, and the duration of heating all played roles. A small pot heated by a single candle might reach temperatures of 200 degrees Fahrenheit or more on its inner surface. The outer surface would be cooler but still warm enough to provide substantial radiant heat. Some soldiers refined the design by using two pots, a smaller one inverted over the candle and a larger one inverted over the smaller one. This created an insulating air gap between the two layers. The inner pot became very hot, while the outer pot remained at a moderate temperature. The gap between them created a convection current, air entering at the bottom, rising past the hot inner surface, and exiting through the top. This moving air distributed heat more evenly and increased the total heat transfer from the system. The dual pot arrangement also provided a safety advantage. The outer pot was cool enough to touch, reducing the risk of burns in the confined and dark space of a foxhole. The inner pot, though extremely hot, was protected by the outer layer and less likely to be accidentally contacted. Finding clay pots in a combat zone was not always straightforward. In agricultural areas, abandoned homes and farms might yield flower pots or similar clay vessels. In some cases, soldiers used other ceramic items, clay bowls, pottery containers, even tiles arranged to create a similar effect. The specific shape mattered less than the material and the general principle of using clay to convert convective heat into radiant heat. The candle fuel was sometimes an issue. Official candles were not always available through supply channels. Soldiers would save candle stubs from any source, accumulate wax from packaging materials, or even make crude candles by dipping string into melted wax repeatedly to build up layers. These improvised candles burned less cleanly than manufactured ones, but still provided the sustained flame needed to heat the pot. The amount of heat produced by a flower pot heater was modest in absolute terms. It would not warm a large space. But in a small, partially enclosed foxhole, the effect was noticeable. A soldier sitting near the pot would feel warmth on the side of his body facing it. This warmth was enough to make rest possible. Enough to reduce the constant shivering that exhausted energy reserves. The system was quiet, unlike a burner with moving flames, or a fire with crackling wood. The flower pot heater operated in near silence. The candle burned steadily without sound. The heated pot simply radiated warmth. This silence was valuable in positions where noise discipline was as important as light discipline. The light from the candle beneath the pot was largely contained. Some glow would escape from the bottom gap where air entered, but it was minimal and could be further shielded with cloth or positioned such that the light faced away from enemy observation. This made the flower pot heater one of the more covert heating methods available. The smell was primarily that of burning wax or whatever fuel the candle used. This smell was present but not overwhelming. In a covered foxhole with adequate ventilation, it dispersed reasonably well. The key was ensuring enough airflow to prevent build-up of combustion products, while not allowing so much airflow that all the heat escaped. The physics underlying the flower pot heater can be described mathematically, though soldiers did not perform these calculations. The radiant heat transfer follows the Stefan Boltzmann law, where heat emission increases dramatically with temperature. A pot at 400 degrees Fahrenheit emits far more radiant energy than one at 200 degrees, following the fourth power of temperature. This meant that getting the pot as hot as possible, without cracking it, maximised the heating effect. The emissivity of clay is approximately 0.91, meaning it converts absorbed heat into infrared radiation very efficiently. This high emissivity made clay ideal for this application. Metal pots, by comparison, had lower emissivity and would have been less effective at radiating heat despite potentially reaching higher temperatures. The practical use of a flower pot heater fit well into the watch rotation schedule. During the early evening, when one soldier was on watch and the other was preparing to sleep, the candle would be lit and the pot positioned. By the time the sleeping soldier settled in, the pot would have reached operating temperature and would be radiating warmth. The candle might burn for 1 or 2 hours depending on its size, after which the pot would continue radiating stored heat gradually. This meant the sleeping soldier received warmth during the critical early hours of his rest period, the time when his body was settling into inactivity, and when cold would be most likely to prevent sleep. By the time the pot had cooled completely, the soldier might have managed to fall asleep, and his body's reduced metabolic rate during sleep would somewhat reduce the perception of cold. The flower pot heater required some maintenance and attention. The candle had to be positioned correctly. Too close to the pot and it might not get enough oxygen. Too far away and the pot would not heat efficiently. The pot had to be stable so it would not tip over, and someone had to monitor the candle to extinguish it when it had burned down sufficiently, both to conserve remaining wax and to prevent the unattended flame from becoming a hazard. Despite these requirements, many soldiers considered the flower pot heater one of the most effective improvised heating methods. It provided sustained warmth, operated quietly and with minimal light, used readily available materials, and required no special skills to construct or operate. The warmth it delivered made the difference between fitful, shivering rest and actual sleep. The technique was not documented in official manuals. It spread through informal channels, one soldier showing another, veterans teaching new arrivals, techniques passed along through the network of soldiers who shared the common goal of surviving winter nights. This unofficial knowledge transfer was how many survival techniques spread through military units, operating parallel to official training and doctrine. The flower pot heater represented an understanding of heat transfer that may have been intuitive rather than technical for most soldiers. They may not have known the terms convection and radiation, but they understood that the pot held the heat and sent it out rather than letting it go straight up. This practical understanding was sufficient to employ the technique effectively. In the hierarchy of heating solutions, the flower pot heater occupied a special position. It required more setup than simply lighting a fuel tablet. It required finding a pot, which was not guaranteed. But once established, it provided more sustained warmth than most other methods. For soldiers who would be in one position for several days or weeks, the effort of finding a pot and setting up the system was justified by the improved comfort it delivered night after night. The sensation of warmth from a flower pot heater or any radiant source is fundamentally different from the warmth of heated air. Understanding this difference, even in practical rather than technical terms, help. Soldiers use their limited heating resources more effectively. When air is heated, it expands and rises. This is convection, the movement of heat through fluid motion. In a foxhole, heated air would rise to the highest point in the space, accumulating at the ceiling or against the underside of a log cover. The soldier, positioned lower in the space, remained in the cooler air that settled toward the floor. He was surrounded by warmth above him but felt little benefit from it. This is why traditional heating methods, fires, stoves, heated air systems, are relatively inefficient in spaces with vertical dimension. The heat goes up, and unless there is active circulation to bring it back down, the lower portions of the space remain cold. A soldier could be sitting in a foxhole where the air near the ceiling was 60 degrees warmer than the air at floor level, yet still be dangerously cold. Radiant heat operates differently. It does not heat the air at all, at least not directly. Instead, it travels as electromagnetic radiation, infrared light, invisible to human eyes but detectable by skin as warmth. This radiation moves in straight lines from the emitting surface to any surface it strikes. When it strikes human skin, it is absorbed, and that energy becomes heat in the tissue. The experience of radiant warmth is immediate and localized. A soldier facing a heated flower pot would feel warmth on the side of his body facing the pot, even if the air temperature around him remained cold. This warmth was real and measurable. His skin temperature would rise, blood flow to the surface would increase, and the sensation of cold would decrease significantly on the radiated side. The intensity of radiant heat decreases with distance following the inverse square law. This meant that the warmth was strongest close to the heat source, and diminished rapidly with separation. A soldier sitting 1 foot from a heated pot would receive 4 times as much radiant heat as one, sitting 2 feet away. This encouraged positioning oneself close to whatever heat source was available. The radiant heat also depended on having clear line of sight between the hot surface and the skin. Anything blocking the path would absorb the radiation and prevent it from reaching its intended target. This meant that to maximize warming, soldiers needed to expose as much skin surface as practical to the radiant source. Hands held out toward the warmth, face turned toward it, body positioned to present maximum area. All of these adjustments increased heat absorption. Clothing complicated this slightly. Fabric blocked some infrared radiation, while allowing some to pass through. Heavy wool blocked more than thin cotton. But even through clothing, radiant heat could be felt. The fabric itself would warm from absorbing radiation, and this warmed fabric would then conduct heat to the skin beneath. The effect was less direct than radiation striking bare skin, but still beneficial. The human body's perception of temperature is complex. We do not sense absolute temperature, but rather heat flow. When heat is leaving our body rapidly, we feel cold. When heat loss is reduced, or when we're gaining heat from external sources, we feel warm. This is why radiant heat from a relatively modest source like a heated flower pot could feel so significant. It was changing the direction of heat flow, turning a situation of constant heat loss into one where some heat was being received. The colour of surfaces affected radiant heat absorption. Darker surfaces absorb more infrared radiation than lighter surfaces. A soldier wearing dark clothing would absorb radiant heat more efficiently than one in light-coloured garments. This was rarely a conscious consideration in the context of winter camouflage and issued uniforms, but it represented another variable in the thermal equation. The pot itself continued radiating heat for an extended period after the flame beneath it was extinguished. Clay has relatively low thermal conductivity, which means it releases stored heat slowly. A pot that had been heated to 400 degrees Fahrenheit might take an hour or more to cool to ambient temperature. Throughout this cooling period, it continued to emit infrared radiation, though at decreasing intensity as its temperature dropped. This extended radiation period was valuable for sleep. A soldier could heat the pot during the evening watch, extinguish the candle when he was ready to sleep, and still receive radiant warmth for the first hour or more of his rest period. This warmth during the transition into sleep was often sufficient to allow the body to relax and actually achieve rest. The mathematics of radiant heat transfer showed why temperature mattered so much. The Stefan Boltzmann law states that radiant heat emission is proportional to the 4th power of absolute temperature. This means that a surface at 500 degrees Fahrenheit emits roughly twice as much radiation as one at 300 degrees, even though it is only about 40% hotter. Small increases in pot temperature resulted in large increases in radiant heat output. In practical terms, this meant it was worth waiting for the pot to heat thoroughly before relying on it for warmth. A pot that had been heating for 30 minutes would radiate far more than one heated for only 10 minutes. Soldiers learned this through experience. The longer the heating period, within reasonable limits, the more effective the subsequent warming. The efficiency of the flower pot heater system came from this conversion of convective waste heat into useful radiation. The candle would have burned regardless, producing the same total energy. Without the pot, most of that energy would have risen as hot air and dissipated uselessly. With the pot, a significant fraction was converted into radiation that actually warmed the soldiers. This increased efficiency meant that a given amount of fuel, so a single candle, could provide more useful warmth. There were limits to this approach. No amount of clever arrangement could create more total energy than the fuel contained. A candle holds a certain number of calories of chemical energy, and that determines the maximum possible heat output regardless of how efficiently it is captured and delivered. The flower pot heater was not creating energy. It was simply making better use of the energy already being released. The sensation of warmth from radiant heat also provided psychological benefit beyond the physical warming. The ability to feel warmth, to sense heat reaching the body, created a perception of comfort that went beyond what thermometer measurements might show. A soldier might still be in a foxhole at 20 degrees Fahrenheit, but if he could feel warmth on his face and hands from a radiant source, his psychological state improved significantly. This psychological component of warmth should not be dismissed as mere perception. Mental state affects physical survival. A soldier who feels less desperate, less overwhelmed by cold, maintains better judgment and decision-making. He's more likely to perform necessary tasks, checking equipment, maintaining watch discipline, caring for his feet. The warmth, both physical and psychological, contributed to overall survival probability. The radiant heat also created what might be called thermal refuges within the cold environment. A soldier could not warm the entire foxhole to comfortable temperature, but he could create a small zone near the heat source where warmth was available. By moving into this zone periodically, warming himself for a few minutes, then returning to other tasks or positions, he could manage his body temperature more effectively than if no heat source existed at all. This concept of thermal refuge extended beyond individual foxholes. In rear areas, soldiers might have access to larger heating sources, stoves in dugouts, fires in protected locations. The pattern remained the same. Cold was the default state, warmth was found in specific locations, and survival involved moving between these zones appropriately. The understanding of radiant versus convective heat was not always conscious or articulate among the soldiers. They did not necessarily think in terms of infrared radiation or inverse square law, but they learned through experience that sitting near a hot object felt warm in a different way than sitting in warm air. They learned that facing the heat source was more effective than turning away. They learned that getting closer made a significant difference. This experiential learning, developed through trial and error in conditions where the stakes were survival itself, created a body of practical knowledge that was in some ways more valuable than theoretical understanding. The soldiers knew what worked. They knew how to position themselves, how long to heat the pot, how to balance fuel consumption against warmth needed. This knowledge, passed informally through the ranks, kept men alive through winter nights. The human body at rest produces approximately 100 watts of thermal energy. This is not much in the context of heating a space, less than a typical incandescent light bulb. But in the confined space of a foxhole shared between two soldiers, this biological heat output became a critical resource. The buddy system existed for tactical and practical reasons that went beyond warmth. Two soldiers could maintain continuous watch through alternating shifts. Two sets of eyes and ears were more likely to detect enemy movement. Two rifles provided more firepower. Two people could support each other in combat, in injury, in the psychological stress of frontline service. But the thermal aspect of partnership was equally important for survival. Two bodies in close proximity could share warmth in ways that solitary soldiers could not achieve. This was not merely about companionship or morale, though those factors mattered. It was about thermodynamics, the physics of heat loss and heat retention in extreme cold. When two soldiers lay side by side under shared blankets, Their combined heat output warmed the space between them more effectively than either could warm himself alone. The air trapped under the blankets, between the bodies and above them, became a thermal buffer. Each soldier's body heat contributed to warming this shared air, and both benefited from the increased temperature. The rate of heat loss from a body is proportional to the temperature difference between the skin and the surrounding environment. When the environment is slightly warmer due to a partner's body heat, the rate of heat loss decreases. This means each soldier's body could maintain its core temperature with less metabolic effort, conserving energy that would otherwise be spent on shivering and heat production. The positioning of two bodies mattered significantly. Lying back to back provided minimal shared warmth. Most of each person's body surface was still exposed to cold air. Lying face to face was more intimate than most soldiers preferred unless they were very close friends. The most common arrangement was side by side, shoulders touching, sharing blankets pulled over both bodies. This side-by-side position allowed each soldier to maintain some personal space, while still benefiting from shared warmth. The contact along the shoulders and upper arms created a zone of skin-to-skin heat transfer through clothing. The shared blanket created a continuous envelope of warmer air above both bodies. The arrangement balanced thermal efficiency with psychological comfort. Some soldiers, particularly in the most extreme cold, would alternate positions through the night. One partner would lie with his back against the other's chest and stomach, the warmer partner wrapping his arms around the colder one. After some time, they would switch positions, the newly warmed soldier providing heat to his partner. This rotation ensured both maintained adequate body temperature rather than one becoming dangerously cold, while the other remained warm. The watch rotation complicated this thermal sharing. When one soldier was on watch, sitting up and alert, he was not contributing his body heat to his sleeping partner. The sleeping soldier lost access to that warmth, making sleep more difficult. Some pairs developed arrangements where the watching soldier would sit close to the sleeping one, maintaining some contact even while performing his duty. The buddy system also formalised responsibility for each other's physical condition. Partners checked each other for signs of hypothermia, uncontrollable shivering, confusion, slurred speech, unusual behaviour. These signs were easier to detect in a partner than in oneself, particularly as hypothermia itself impairs judgment and self-awareness. Frostbite was another danger that partners monitored for each other. Extremities, fingers, toes, ears, nose, were vulnerable to freezing in extreme cold. A soldier might not notice his own fingers growing numb and white, but his partner could observe these changes. Early detection allowed for rewarming before permanent tissue damage occurred. The rewarming protocol for frostbite involved skin-to-skin contact with a warmer body part. A soldier with frostbitten fingers would be instructed to place them against his partner's stomach or under his arms, areas where body heat was reliably present. This direct heat transfer could reverse early frostbite, restoring circulation before cells died. The partnership made this treatment possible in ways that solitary survival did not. The foot care routine depended on mutual accountability. Soldiers were supposed to remove their boots twice daily, dry their feet, check for signs of trench foot, and apply protective oils. Left to individual discipline, this routine was often neglected, removing boots in extreme. Cold was unpleasant and exhausted soldiers frequently skipped maintenance tasks. But when partners made each other responsible for foot care, compliance increased dramatically. One soldier would check his partner's feet, ensuring the boots were removed, the socks changed, the skin dried and treated. This mutual oversight prevented many cases of trench foot that would otherwise have removed soldiers from duty for weeks or months. The bond that formed between foxhole partners was intense and often lifelong. Sharing a hole for even a single night created connection. Sharing one for days or weeks created relationships that transcended normal friendship. These men knew everything about each other, sleeping habits, fears expressed in darkness, private thoughts shared during long watches, the contents of letters from home. The intimacy of the arrangement was unavoidable. In an 8x4 foot hole, there was no privacy. Every movement was felt by the other occupant. Every sound was heard. Every smell was shared. Some soldiers adapted easily to this closeness. Others struggled with it but accepted it as necessary for survival. The trust required was absolute. A sleeping soldier was completely vulnerable. He depended on his partner to watch for enemy movement, to wake him for his watch shift, to alert him to danger, to care for him if he became injured or sick. This level of dependence created bonds that in some cases became the strongest relationships of the soldiers' lives. The shared warmth extended beyond the physical. There was psychological warmth in not being alone, in the isolation of the front lines where each foxhole could seem like the only inhabited space in a vast empty landscape. Having a partner meant having evidence that human connection still existed. The sound of another person breathing, the weight of another person beside you, these sensations confirmed that you were not entirely alone in the darkness. Communication between partners was often minimal. After days or weeks together, much could be understood without words. A shift in position might signal readiness to switch watch duty. A particular sigh might indicate frustration or fear. Partners learned to read each other's states and moods, responding without need for verbal exchange. Some partnerships were temporary, lasting only until one soldier was rotated out, wounded or killed. Others persisted through the entire war, the same two men sharing foxholes across multiple campaigns and countries. The longer the partnership lasted, the more efficient the cooperation became. Partners developed routines, understood each other's preferences and worked together with minimal friction. The loss of a partner was traumatic beyond the general trauma of combat casualties. It meant losing not just a friend, but the person who kept you warm, who watched while you slept, who knew your fears and hopes. It meant being assigned a new partner and having to rebuild that relationship from the beginning, learning new patterns and establishing new trust. The buddy system as thermal strategy was never formally taught in those terms. Training manuals might mention the value of partnering for watch rotation and mutual support, but they did not explicitly state two bodies produce twice the heat of one body. Soldiers learned this through experience, through cold nights when having a partner made the difference between achieving sleep and shivering through the hours. The efficiency of two-person thermal sharing had limits. 3 people in a foxhole did not continue the pattern. The space became too crowded for effective rest, and the marginal warmth gained did not justify the reduced mobility and increased discomfort. 2 was the optimal number for both tactical and thermal purposes. The shared warmth of partnership represented the most reliable heating system available to frontline soldiers. Heat sources could fail. Candles could burn out, fuel tablets could become exhausted, improvised burners could malfunction. But as long as both partners remained alive and conscious, their bodies continued producing heat. This biological furnace, shared between 2 people working to keep each other alive, formed the foundation of winter survival. The feet were the most vulnerable mechanical component of the soldier system. They carried the full weight of the body plus equipment. They stood in mud, snow, and standing water for hours or days. They were confined in boots that rarely dried completely, and they were far from the body's core, making them susceptible to reduced circulation and cold injury. Trench foot was a non-battle injury that could remove a soldier from combat as effectively as any wound. The condition developed when feet were exposed to cold, wet conditions for extended periods, as short as 12 hours in some cases, though typically requiring a day or more of continuous exposure. The damage was progressive and insidious. The initial symptoms were relatively mild. The feet would feel cold and numb. The skin might appear pale or slightly blue. These signs were common enough in winter conditions that they often went unremarked. But if the exposure continued, the condition worsened rapidly. Blood vessels in the feet would begin to deteriorate. The tissue would swell as fluid leaked from damaged vessels. The skin would become red or purple, painful to the touch. Blisters might form. In severe cases, the tissue would begin to die, gangrene setting in as blood flow ceased entirely. At this stage, amputation might be necessary to prevent the infection from spreading. The time from initial symptoms to severe damage could be surprisingly short. A soldier who ignored early signs might find himself unable to walk within 24 hours. The pain became excruciating. The feet would swell so much that boots could not be put back on. Evacuation to rear area medical facilities was the only option, and recovery took weeks to months. The military took trench foot seriously because the numbers were staggering. In some units during winter operations, non-battle casualties from trench foot exceeded battle casualties. Entire companies could be rendered ineffective not by enemy action but by a preventable medical condition. This represented a significant waste of military resources. Trained soldiers removed from combat by a problem that proper foot care could largely prevent. The prevention protocol was straightforward in theory but difficult in practice. Soldiers were instructed to remove their boots twice daily. The feet should be dried thoroughly, massaged to restore circulation, and inspected for signs of damage. Clean dry socks should be put on. Whale oil or similar protective grease should be rubbed into the skin. The feet should be elevated for a period to allow blood flow and air circulation. In practice, this protocol faced numerous obstacles. Removing boots in a foxhole in winter meant exposing the feet to freezing air. The act of removing wet boots was itself painful when hands were cold and stiff. Finding a clean, dry pair of socks when everything was damp was often impossible. The whale oil might be frozen solid or simply not available through supply channels. The psychological barrier was also significant. Boots provided a sense of security and readiness. If enemy action required immediate movement, a soldier without boots was helpless. This meant that removing boots felt dangerous, even when intellectually the soldier knew foot care was important. The temptation to skip the routine, to keep boots on and accept the discomfort, was strong. This is where the buddy system proved critical. When partners made each other responsible for foot care, the routine was more likely to be followed. One soldier would insist that his partner remove boots and perform the maintenance, overcoming the individual's reluctance. The partnership created accountability that individual discipline often could not maintain. The procedure itself was methodical. The soldier would unlace his boots if his fingers had enough dexterity, which was not always the case in extreme cold. The boot would be carefully removed, pulled off gently if the foot was swollen or the boot frozen to the sock. The sock would then be removed, exposing the bare foot to air. The inspection began immediately. The skin colour was noted. Pale white indicated insufficient blood flow. Blue or purple indicated more severe vascular problems. The temperature of the skin was assessed by touch. The soldier would check between the toes, where moisture accumulated and tissue damage often began first. Any blisters, cuts, or areas of unusual appearance were noted. If the foot appeared normal, the maintenance continued. The foot was dried using a relatively dry cloth, or the inside of a cleaner garment. This drying was thorough, ensuring no moisture remained between toes or in the creases of skin. The motion of drying also served to massage the foot, stimulating blood flow. The whale oil application came next. This was not pleasant. The oil was cold, greasy, and had a distinctive fishy smell, but it created a barrier that protected skin from the deteriorating effects of constant moisture. The oil was rubbed thoroughly over all surfaces of the foot, including between toes and around the heel and ankle. A fresh sock would then be put on if available. If no fresh sock existed, the least damp of the available socks was chosen. Many soldiers carried 3 pairs of socks for rotation. 1 pair worn, 1 pair drying somewhere on the body, often tucked inside the uniform against the stomach or chest where body heat would gradually dry them, and 1 pair ready to wear. This rotation ensured that the sock being put on was drier than the one being removed. The boot was then replaced, carefully laced to provide support without restricting circulation. Boots that were too tight exacerbated circulation problems. The soldier had to find the balance between loose enough for blood flow and tight enough for effective walking. The removed damp sock joined the drying rotation. It would be placed against the body or hung in a relatively warm area if such existed. Over the next several hours, body heat or ambient warmth would evaporate some of the moisture, making the sock ready for the next rotation. This entire process might take 10 to 15 minutes per foot. For a soldier exhausted from combat, cold and sleep-deprived, this time investment seemed enormous. The temptation to skip it or rush through it was constant, but the partners enforced it on each other, knowing that a partner who developed trench foot was both suffering unnecessarily and becoming unable to contribute to their mutual survival. The elevated rest period was also important. After the feet were dried, treated and re-socked, They should ideally be elevated, raised above the level of the heart to improve blood flow, and reduce swelling. In a foxhole, this meant lying on the sleeping shelf with feet propped on a pack or folded blanket. Even 10 minutes of elevation made a measurable difference. The sock drying technique using body heat was particularly clever. The stomach area, protected by layers of uniform and equipment, maintained relatively consistent warmth. A damp sock placed against this area would gradually dry from the heat without requiring any external energy source. The soldier became his own drying apparatus, using otherwise wasted body heat to maintain his equipment. The frequency of foot care was debated. Official guidance recommended twice daily, but this was often impractical. Once daily became the more realistic standard for frontline soldiers. Even this reduced frequency required discipline and mutual enforcement through the buddy system. The cases of trench foot that did occur served as powerful lessons. When a soldier in a unit developed severe trench foot, his condition became visible to others. The swelling, the discoloration, the obvious pain, all of this demonstrated the consequences of inadequate foot care. Units that witnessed severe cases became more conscientious about prevention. Some soldiers developed more serious circulatory problems. Frostbite could damage tissue quickly when temperatures dropped below freezing, and wet feet accelerated heat loss. The rewarming protocol for frostbitten feet required careful attention. Rewarming had to be gradual and controlled to prevent additional damage. The partner would help with frostbite rewarming when it occurred. The affected foot might be placed against the partner's stomach or held between the partner's hands. This skin-to-skin contact provided controlled warmth. The rewarming was painful. The sensation returned to frozen tissue. Intense burning and aching developed. But this pain meant the tissue was alive and recovering rather than dying. The loss of feet to cold injury represented catastrophic personal and military consequences. A soldier without functional feet could not walk, could not fight, could not contribute. He required evacuation and prolonged medical care. He might face permanent disability or amputation. All of this from a condition that was largely preventable through consistent daily maintenance. The ritual of foot care became one more element in the complex choreography of foxhole survival. It competed for time and energy with other necessary tasks, maintaining watch, cleaning weapons, preparing food, catching sleep. But it was non-optional. The soldiers who maintained discipline with foot care had higher survival rates and longer combat effectiveness than those who neglected it. The psychological aspect of foot care should not be overlooked. The routine itself, the methodical process of removal, inspection, treatment, and replacement, provided a sense of control in an environment where control was largely absent. The soldier could not control, the weather could not control enemy action, could not control when he would be fed or relieved. But he could control his foot care routine. This small agency mattered for maintaining mental health. The smell of whale oil in a foxhole became associated with survival and discipline. It was an unpleasant smell, but it meant that foot care was being performed, that the soldiers were taking the necessary steps to prevent injury. In some ways, that smell represented hope, the intention to survive long enough that healthy feet would be needed. The partnership aspect of foot care created vulnerability and trust in equal measure. Removing boots in the presence of another person, exposing feet that might be damaged or simply unwashed for days, required a level of comfort with that person. This vulnerability strengthened bonds. The partners saw each other in states of physical weakness and need, and the trust built through these moments extended to all other aspects of their relationship. The feet, though far from the consciousness during many moments of combat or survival, represented a critical system that required active maintenance. The ritual of care, enforced through partnership and supported by available materials, prevented catastrophic failure of that system. Through this combination of knowledge, discipline, and mutual support, soldiers kept themselves mobile and functional through conditions that would otherwise have destroyed their ability to walk within days.